Here we are again, logic for computer science, classical and non-classical, Springer 2019. This is our textbook, and I'm the author. And today we have chapter 2, which is really intuitive introduction to classical logic and semantics, as the title says, but I wrote it in order for people who might not have had any or not much contact with logic. So this is really introduction, intuitive introduction with some formalism, of course. So the real, strict course starts in chapter 3. So, we have 6 parts. First, classical logic model, propositional languages, propositional semantics. All is classical. Examples of propositional tautologies, and then we will have introduction to predicate language and predicate tautologies. So, a classical logic model. And now I'm going, here I write, I like the slide because it's the shortest history of logic. You start at Stoic school of philosophy, 3rd century before Jesus Christ, and now you move fast to mid-19th century. English mathematician Bull, who is, I brought him because he's sometimes regarded as the founder of mathematical logic, and first axiomatic system, because we are going to talk about proof systems, 1879 by German logician Frege. And now I'm saying very slowly, because that is really what logic is in a simple way. Logic builds symbolic models of our world. And logic builds the models in order to describe formally the way we reason in and about our world. And also poses questions about correctness of such models and develops tools to answer them. And that's what we are going to do in our course, and that's what the book sets up, all these pieces. And of course, when you develop a logic, you have to make some assumptions, so because they are very strict models and very special models. So assumption 1, classical logic admits only 2 logical values. And of course, why? Because it was created to model reasoning of mathematics. So that's why it's black and white, because of course we want mathematics to be black and white. So we want a mathematics to be always true or false. So that's why the logic has only 2 logical values. And now the language which we reason uses what's called sentences. And whatever is the sentences are the smallest pieces, let's say. And the way we build it using certain phrases, like not true, and, or, implies, if then, from the fact that we can deduce, equivalent. So these are the special phrases we use to build more complex sentences from the very simple sentences. And of course, logic is symbolic, so we use symbols to denote the basic assertion and all those words and phrases, and that's why we talk about symbolic logic. And also, logic studies behavior of those special words and phrases, and of course, they have intuitive meaning. So logic builds models to formalize this intuitive meaning of those words and phrases. And we do so, to do so, we define first formal symbolic languages, and then we define the meaning, formal meaning of the symbols of that symbolic language. And that formal meaning is called semantics. And of course, symbols, we choose symbols. I will show you how different symbols which had been used or I use in the logic. But as I say, in the language we are using, I use the following symbols. And I use this one symbol, I use this symbol, I use this symbol, and I use that symbol. And this is for not true. This is for and. So this we read and. That is for if, then, and other. We deduce, etc. So these are the natural, that's how we read. So these are the phrases in natural language, and that is the symbols, and that is if and only if or equivalent. So, and also those symbols has names, and so this is how we read them. And the names, this is a name, names are negation. This is called conjunction. This is called implication. And this is called if and only if, or equivalence, equivalence. I like the word equivalence. So, so these are the names, and those symbols are called propositional connectives. Propositional connectives. Those symbols are called propositional connectives. And so the basic components of propositional logic are propositional language and propositional semantics. Those connectives and the way we read the symbols we use is a language. And okay, now also, so this is propositional part. We also use quantifiers, and we have two symbols for quantifiers. Quantifiers, I want to. So we use the symbol like this for universal quantifier, and it reads for all, every, etc. And this is existential quantifier, and it reads some. So we read it as some exists, there is. So I say, here is the symbol, this is how you read them, and in natural language, if you say for all, if you want to build your logic model of your natural language phrases or sentences, you if you say for all, you replace by a symbol of the universal quantifier. And these are, if you add those symbols and some more symbols, is called predicate logic. So the basic components of predicate logic are, again, predicate language, which is richer, and predicate semantics. And of course, predicate logic is much more complicated model. And we develop here intuitively enough for you to later to understand the full formal model. So propositional language is quite simple. So for example, you have natural language. It's a natural language which uses some mathematical symbols. If 2 plus 2 equals 5, then, so what you do, you see first which are our basic assertions. That is our basic assertion. And if then is our implication. So you have a symbol for that. So you denote basic assertion by small letters like A, B, C. They are called propositional variables. And that natural language sentence would become, in our formal language, A implies B, and we put the parentheses around, and I will explain you why we always put parentheses. So this is a natural language sentence, and here we have a propositional language statement, which is called a formula. So in our logic model, natural languages are represented in different ways by formulas of the formal language, in this case in propositional language it's called. And of course, I give you exercise how you do when you have a complex statement, how you translate this natural language. It's natural mathematical language, but it's natural language. There are some mathematical statements in that into propositional language formulas. So how you do it? You do the steps. First, identify all words and phrases representing logical connectives. So these are your logical connectives. So the word representing this is a name, is a negation, but is not true, etc. So you see this is, and so you identify your phrase or your names of your connectives. Like here would be, it's not true, so that would be negation. Now you say at the same time, because I will explain you why you have to put parentheses. But another is and, because here it's your and. So you identify and what you want later to replace that and by the symbol 8. Not true, replaced by the symbol A. And what implies, so implies is you replace that structure by implication. So, and also you identify words and phrases represent the connectives, and the rest is, so in a sense you can say that this sentence, you can already write it, that if, not, and that was at the same time, that's why we put parentheses, then, so this is like more structured way of writing your sentence. And now you can see that you replace your connective if then those phrases by, that would be implication, and not by negation. And this are basic, they are called basic assertion in propositional basic assertion, and we replace them by letters which are called propositional variables. So this assertion, 2 plus 2 equals 4, is replaced by a variable a, and that is by b, it's a different statement, and we write the propositional formula in the language. It means we look how that natural language sentence is built with using all those phrases and basic assertions. Those basic assertions, they're not that basic and they can be more complex. For example, I can give you such statement: if for all natural numbers n greater than 0, n plus 1 equal 5, then I am Anita. It's a statement, nice sentence. So, and I want to translate that statement in our propositional language. So when you look at this, what you have, that you have this whole becomes a basic statement, because in the language, in the propositional language, you do not have means to represent for all natural numbers, etc. So, but from propositional point of view, you would have only that would be A, and the connective is if, then, and that would be another, just a propositional statement B. So the translation would be A implies B, and this basic statement can be very, very complex from propositional point of view. That's why if we have a predicate language, the predicate language would have here quantifiers and you could go inside. But from our propositional point of view, the whole thing is a basic statement. So, and the formal description of symbols and definition of the set of formulas is called a syntax. So syntax stresses that formula, the word syntax stresses that the word formulas do not carry neither formal meaning nor logical value. It's just this, how you build those sentences from the symbols you have available. And of course, the semantics, what does it mean? Is it true? And when it is true, what does it mean that is true or false? That would be semantics, and we will assign semantics to that later. And so, let's now try to write it in a little bit more sophisticated way. So we can think about natural language, which have everything, as a set of words, let's call W, and of all W's words and sentences based on given alphabet. Right? You have alphabet and you have all words of sentences, different alphabet, different languages have different, and then you build. So I could say it's a very simple model, but I can say that natural language is alphabet and all the words of that and W is not only words, words and sentences. So what you build out of that alphabet. There are words, sentences, books, everything. So, of course, this is not very, it's a little bit too general, but we will have a little bit more, we introduce a little bit more to that model to be able to define what is a sentence. For example, that would be a kind of a sentence, which is called a formula. So, and also, of course, we want to define it in the way that we can recognize, does it belong to this language or that language? So, so symbolic, now, so we define the symbolic language as a pair, as symbolic language is alphabet. But we have the set of formulas. And the formulas, we define it in a way that we can recognize well if somebody is a formula or not. And now our goal is, and also once you have it, so let's say symbolic language, I will write it because I'm going to talk about it now, that symbolic language I want to have symbolic language is alphabet and F is as a pair. So that's how we write to. These are called formulas, and this is called alphabet. And we define now what are formulas in a precise way, because we want to be able in symbolic language to recognize what is a formula, what not. Now, and also in symbolic languages, we have two categories. One are propositional languages, and two are predicate. And we already talked about, right? Propositional languages would have a different alphabet, and predicate languages would have a different alphabet, and then we will have to define the formulas out of the proper alphabets of those languages. So, propositional language definition, you see we have first definition. A propositional language, we understand a pair where A, and F, when A is called propositional alphabet and F is called well-formed formulas. We say formulas because it's a long statement, but we define it as the set of all well-formed formulas because we want to be extremely precise. What is a well-formed, what isn't. So you can think is a grammar of that language, very, very precise, little grammar. So alphabet, as we already sort of have the intuition, we have the propositional variables, and they represent those basic statements, and we use symbols. So for propositional variables, we use A, B, C, P, Q, R, and if there's too many of them, you put the indices, because if you have 5,000, you say A1, A2, etc. So they're called propositional variables. And of course, we have propositional connectives. We already know what they are. Their names are negation, conjunction, disjunction, implication, and equivalence, which is also called biconditional. And also we add parentheses. Remember, we were writing A and B, and I said that we always put parentheses around. So this is a conjunction, propositional, and that would be our well-formed formulas. with parentheses, so because we define them with parentheses. And now the set we have already alphabet. Alphabet is those symbols of connectives. This is all propositional language. And set of all formulas is recursively. So we have all variables are formulas. They're called atomic formulas. And the recursive step, if we have formulas, then such expressions are formulas. What is important here, and then I want to bring, and I will be repeating it. So now we define the set of formulas F, and we'll have our language is alphabet, and I define now formulas, variables are formulas, and we denote variables by a small letter. Now, if you have more complex, and you have a connectives, because we have all those connectives, and now formulas are built out of those connectives and variables in a special way. And we have that if you have A is already formula, A, B, A and B is a formula, etc. Here you have capital letters. Capital letters. So if you use the capital letters, it means that can be a very complex formula. For example, A or not B is a capital letter. A is also can be capital letter because all variables are formulas. So if you that can be our formula A, and then if I have another formula B, for example, B, let's say, is C, because variables are formulas, that says that A and C, and you put parentheses around, is your formula. So I want to stress that when you see a capital letter, it can be a complex formula, a complex expression built out of our alphabet and connectives in a certain way. And if you use the small letters, this is only for variables. And now what I said, that some of expression you write are proper formulas, some are not. And you recursively you construct them. For example, why we use those in definition, why we use those parentheses, because if you had written this A and B or A, when you say A and B or A, you do put by your voice and intonation, you put the parentheses. So I said A and B or A, it means that would be but also, even if you write like this, that could be this formula or that formula. So to be exact, which one, you put the parentheses around it. So, for example, here's nice exercises that if you see the sequence like this, is this a well-formed formula or not? So, and how you, and also you can read it. Look, you have a formula, you have something like that. Of course, it's not a well-formed formula because what? This outside parenthesis is missing. Because by formula, you always put, you close it by parentheses. So you know exactly where it starts and where it finishes. And then you can say, what does it say? This says, it is, if it is not true then A, then we have A or B. I put we have, just to put we have A or B, to put those parentheses in my natural language. So so the structure is very precise. And and then you can have a nice exercises how you have, I gave you plenty, so it's a nice way to play. We have a complex statement. One likes to play bridge, or from the fact that the weather is good, we conclude the following. One does not like play bridge, or one likes swimming. That's a natural language sentence. That is a formula which represents that natural language. And you know how to think about it, because your formula, you look which are your connectives, and then the rest are your basic statements. So in this is, you have the basic statement, one likes play bridge. There is no connective inside. That is weather is good. That is basic statement because there's no connective inside. It means there's no a word and, if, and so on. And then the third one like swimming, and then you have the formula. And also, as I said at the beginning, we will be using these symbols for connectives. They are different symbols for connectives. So I listed you other symbols. Historically, they were this symbols NA, DAB, CABI. These are called that is the language without parentheses. And that was invented by a Polish logician, Łukasiewicz, and is called as Polish notation, not because to say that the Poles were whatever first to discover such notation, but his name was Jan Łukasiewicz, and it was impossible to say Łukasiewicz, and they said, oh, Polish. So in this way you have a Polish notation, and of course that is Hilbert, Peano, Russell, Schroeder, Perth. So there are different disjunctions. There are different ways you write the symbols for all those connectives: negation, disjunction, conjunction, implication, equivalence. There are different symbols. We will be, I say, if you define the language, you say, these are my symbols, and that consistently will be using those symbols. Not, but these are also pretty good symbols. And you can see historically, you know, they like to use plus, multiplication for and. It's not the best, but it was, and so on. The words conjunction and C for conjunction came late. Okay, semantics. Okay, as I said at the beginning, we model our reasoning with two logical values because we want to have a black and white world of mathematics. The real life would be nice if it was as black and white as mathematics, but it isn't. That's why we'll be also talking about non-classical logics, which describe more complex reasonings, or describe semantics of more complex reasonings than black and white mathematical reasoning. So, and semantics, so semantics is how you assign logical values, how you say that our formulas, you see the language now, we are in symbolic model. Is it true? When it is true, what does it mean it is true? So that is now our goal to assign the logical values to our set of formulas. And we are still in propositional logic, and formal, like really formal definition is given in chapter 3. So, and then you see when you say, when you assign logical values for your intuitive meaning, you have to always convince other people that they agree that is a good way of thinking about, for example, conjunction. This is the easiest one. Conjunction A and B is true. Formula, because now we are in our set of formulas. Now we are in our already model in our symbolic language. We say that conjunction is true if both of formulas are true. That's very, and so if one of is false, the conjunction is false. And now, you see, we can write it as, which is called the truth table for conjunction. It means that if A is true and B is true, conjunction is true. So it's called that, we can express it as conjunction table. Disjunction. Disjunction word is used in natural languages in two different senses. First sense is A or B is true if at least one of sentences is true. And the second is that A or B is true if one of the statements A and B is true and the other is false. So it's like this or that. So that is a different meaning, which we often use in natural language. We use in our symbolic logic, we use word disjunction or the word or in first sense, and that's why we adopt the, that disjunction table, that A, you can see that A, T, T, only F and or F is false. And negation is obvious. Now, implication is more complex. Sometimes in everyday language, a statement, if A then B, is interpreted to mean that B can be inferred or deduced, right? If this, then that, and you deduce, and so on. In mathematics, it's different. We say that, and I will define you how you do it in mathematics. So it means that the value, the logical value of implication would depend only of logical value of the parts of A and B, as it was in a sense of disjunction. The logical value of A or B depend only which logical values were assigned to A and B, and implication would be the same. And so now, look now at this. All right, so I go here. And implication, we define like that. That we say our implication, we say that implication A implies B is false only if truth implies false and is true in all other cases. So that is how we define it. Now, to accept it, this is quite obvious. Nobody would argue that true implies true is true. Nobody would argue that true, if you have true, then you implies false is false. But those two pieces is questionable. You have to convince that really if you have false statement implies true is true, and false statement implies false is true. And now I'm going to give you an example that in mathematics we have that. We have those cases that false implies is true and false implies false is true. So that justifies that our classical implication would be like that. If you put here different values and you convince people to use it, it would be non-classical implication, and we'll talk about non-classical implication and non-classical semantics later. So let's now look at the following simple mathematical theorem. It's nice to use the word theorem, but it's a fact which everybody agrees with, and it was proven in mathematics. For example, for every natural number, n, if 6 divides n, then 3 divides n. If n is divisible by 6, and 6 is divisible by 3, so n is divisible by 3, right? And this is true for all natural numbers. Basic, important fact in arithmetic. So, of course, it's true for all natural numbers, so it's true for 2, 3, and 6. So if you say n is 2, you have a statement, 6 divides 2, then 3 divides 2. That is a false statement. And this is false statement. And the whole thing is true because it's true for all natural numbers. So this is what, say, that is. We have to have this case. Now let's look to justify that in mathematics, false implies true is also true. And here with this, let's, in our theorem, consider number 3. What we get, if 6 divides 3, then 3 divides 3. It means that implication where A is false and B is true, and so that justifies our case. And of course, when you have 6 implies 6, you have true implies true, so you don't need, but you have also justification for that case. So that's why that implication table is accepted as the definition of semantics for our implication. And that's how you learn, you've learned already at high school, or probably. And equivalence is true, both formulas have the same, so that's pretty obvious. And then we can write it in one big truth tables to have everything together if you want. Now, the next things which I want to stress, that the truth tables, when you look at those truth tables, that shows that the propositional connectives is in the value of the formulas independent of the values, what the formulas A, B represent. And so you can write it just as a system of equation. Negation of T is false, negation of false is T and T is T, etc. So, and so we have the equations for the connectives. And now you can have exercise. If you have a formula, show that is F for the values, and then you just put F and T, and you can evaluate the values of the complex formula in terms of the values of which were the values of the formulas which were the big formula was composed of. So that is why the bull is also called a father of classical logic, because that's what Bull wanted. Bull wanted logic to be just evaluation, like algebraic evaluation of logical values. And that fact that we can do it because we set it up is called a property, special property, that the logical value of the formulas formed by the means of our connective and certain given formulas depends only on logical values of the given formulas. That's called extensionality. So, and we say that all propositional connectives are extensional. Of course, you have other propositional connectives like believe, possible, certainly, which are not extensional, and they belong to non-classical logics. And of course, in these terms, you can think that what is a logical connective is a function which, for the formula, assigns another. So you can say that negation for A, if A is true, negation assigns false, but you can have another assignments, for example, for true F, or you can have assignment for true true, and so that would be, they are all extensional connectives because that is only assignment relationship between logical values. And here you have a table of all binary extensional connectives. So I listed the 16 of them, and I listed all of them, and some of them are our logical connectives, and they have special symbols. But you have 16 extensional, possibly you have defined 16 extensional binary connectives, but who would want, if you want to do a logic with such connective, you have to convince people that is to accept it. And it happened that we have only this are special. I'm going to talk about those two extra binary connectives which are accepted and which are called classical binary connectives. And also, the next important notion is called functional dependency. So, functional dependency of connectives is ability of defining some connectives in terms of the others. For example, all classical propositional connectives, all classical propositional connectives can be defined in terms of disjunction and negation. It can be defined also in terms of negation and any other. So if you have only this and this, you can define all the others. If you can have negation and this, you can define all the others. That is called functional dependence. It's a very strong property. And also, we have two binary connectives, which are arrows, which could define all classical connectives. Nice exercise. And also those connectives, because they can define, if you add here those two connectives, these are, now you have all possible connectives. If you add those connectives, which I'm going to define you, they have names, and you can use this one to define all others, or that one to define all the others. So they are very important connectives. And arrow up is called Schaeffer, 1913, and it's called alternative negation. And it reads, A arrow B reads, like implication reads if then, reads not both A and B. And for example, negation is defined as A arrow A. And disjunction is defined as A arrow, and you can use your truth tables for connectives to show that this is good. And the other one was discovered by Łukasiewicz. So it's a Polish connective, which is called joint negation, and it reads neither A nor B. And in 1925, Zielinski proved that no propositional connective from that table of 16 suffices to define all remaining classical connectives. So now the next important notion, so this is semantics. Now you have a formula and you know how to assign logical value to those formulas. The next important notion is notion of tautology. So tautology are such formulas that are always true. You say, oh, tautologically true, it means it's always true, and it means it's in our model, this is always true because of their syntactical structure without reference to the natural language meaning of the propositions that they represent, because that's how you define extensionality of connectives, that's how you define our semantics for connectives. And how you do it, for example, you've seen it already in school. We have formula A implies A, and A can have two possible logical values, and you compute the value of this would be T implies T is T, and you have T and T, so the formula is a tautology. For all possible values of formula A, you always have a T. Now, implication, you can rewrite the truth table for the formula A implies B, and here you can write it like that. And now, so the definition is, for any formula of propositional language, now we have formula of propositional language, A is propositional tautology if all logical values of A, and we write AT, is T, it means we write A equal T, and this is the, so all possible values of the formula A, we have always truth. So, and this is our symbol for tautology. Propositional tautology is our, here, now is A is tautology. And you have a lot of classical tautologies. Some of them are very old. Modus ponens, 3rd century before Jesus Christ, and Socrates, and they all were. Of course, at that time, they were not writing those formulas. There were no formal definition. Formal definition came at the beginning of 20th century, and so they have names, and also with the implication is important. We use the words sufficient and necessary condition. So sufficient, given an implication A implies B, A is called sufficient condition for B to hold, and necessary, given implication B is called necessary condition for A to hold, because you talk about sufficient and necessary condition, so here we spelled it out. And also implications, because implication is very important connective. We say A and B implies B is called simple implication. B implies A is converse, so simple, converse, not B. You have a simple. Not B implies not A is opposite to A implies B, and contrary is not A implies B. So these are words we use. Given implication, give me opposite implication, and we say instead of proving A, I can prove opposite implication because we have a special tautologies. And also you have laws of contraposition, that it means that A implies B is if and only if, not B implies A. So we will call it later logically equivalent. So it means that they are very important because in deductive argument, what does it mean? If I want to prove this, you can be proving not be because they are equivalent. So they are important laws of contraposition, and also the same necessary and sufficient for if and only if, and also we can treat this as a definition, because you can have a language without that connective and you can define it in terms of implication and conjunction like that. And then you have already 3rd century before Jesus Christ, and you have all these modus tollens, tautologies. They have nice, we are 3rd century, and they were given later because they have, the names were given later because they are in Latin. And 1213, Don Scotus, that is very important. Clavius, Frege, we have already 19th century. And again, I already told you at the beginning that Frege is important because he gave first formulation of classical propositional logic as a formal axiomatic system. The next thing which is important, so this is the list. There's a bigger list, and I gave you this list because it's a good training ground. You can show that all the tautologies and so on, but also we will be using freely all of them later. So I will not mention much of it. I will say, oh, this is a basic tautology, so you don't need to prove it. So the next important thing is what is called apagogic proof. So that is a nice statement. Apagogic proofs means proofs by reductum ad absurdum. So you have one strange word defined by the Latin. So it means you prove by reduction to contradiction. So it means reduction to contradiction, to absurd, it means contradiction. To prove that A is true, how we do? We assume negation of A. This is all classical. If we get a contradiction, it means that we have proved A to be true. And correctness of that reasoning, this is important reasoning, is given by that tautology. Assume A, then B and not B, this is a contradiction, then A. And the whole chapter contains, as I already said, the list of basic tautologies. We will use them later, so just play with them, and slowly you'll memorize all of them. So now we move to predicate languages. Of course, predicate language is much more complex and complicated. So, and our alphabet is much richer. And so to define predicate language, here we have. And I'm going to write it because I will refer to it again and again. So now, predicate language is, as before, alphabet and formulas. Alphabet is richer. And we have an additional set, which are called terms, which are going, and these are formulas, and this is our alphabet as it was. So now we have an additional step to define formulas. We do it in the help of something which is called the set of all terms. And of course, we have alphabet, we have propositional connectives, you have quantifiers, as I mentioned before, you have parentheses because we want to have those formulas defined in an unambiguous way, and we have variables. Now, variables are variables. It's more like X is a real number. So these are different. They're called just variables, not propositional variables. So, and now we have also, so we have variables and we have constants. C is the set of constants, like 1 in mathematics, 1, 2, 3, square root 2 is a constant. A variable is x. So, and we have a predicate symbol. Predicate means relation. So, for example, we have x greater than 0. This is a mathematical simple statement. This is a relation between a variable and 0. For some x's, if I say 2, x equal 2, that would be true. And if x equal minus 5, that would be false. So this is how you have variables in mathematics and relations. The variable for certain variable, that relation holds between certain elements. So let's say that x is, for example, a real number. So it holds for one other. So that's, you can see the whole reasoning, and the notion of true or false is more complex, and we want to model that. So first, you can see if you have relation, it gives you true or false. Relation, say, relation holds between two elements or does not hold. So relation are called predicates in a fancy way. So in our language, to model statements and situation like that, we need to have relation. It means predicates. And so now we have part P is set of predicates. And this is, we want to model all possible situations in the whole mathematics and life. So we assume that there is countably infinitely many of those relations. And we write them P1, P2, etc. But going back here, because that is important part, that how you, this is, we want to model, this is my real statement in mathematics, right? So a relation in mathematics is, this is two-argument relation, and we often write it that this is two-argument relation because it holds between a variable x and 0. So we put the relation symbol not in the middle, we put it in front. So like, so we put it in front. So in logic, we put it also in front. So we would say that this is real relation, and this is symbol or predicate representing that relation. So that's why we write the predicates, and then, as I said, that we have a constant. So here in logic, we will have also a symbol. This is a constant in real life, so we will have also a symbol for the constant. So 0 would be represented by certain constant. So let's say, and that would be an atomic formula in our language. So the real way we write, then we write the relation, symbol of relation in front, because it shows that it has two arguments. So, and here to represent this, right? If you want to represent this in logic, that would be P, and this is one constant. And because I represented 0 by C1, would be and that would be a formula, and that would be called atomic formula in predicate logic because it's like the smallest possible formula. And of course you have that is true and false. So that is what the predicate mean. Now, we also, and I explain here, in real life, x minus y expresses that element as small. In predicate language, that's exactly what I just explained to you. And also, we have a functional symbols. When you look at mathematical statement, so we have P are the predicates, relational symbols, P predicates, and represents relations. And now you have fat F, and they are called function symbols. Functions symbols, which represents functions. So, for example, let's x plus 3 equal 5. When you look at nice little mathematical statement, when you look what is a function, what is a relation? This is a relation, and what is plus in mathematics? Plus, let's say, in natural numbers. Plus is a function which takes two natural numbers and returns a natural numbers. So plus is really a function between two numbers, and you write plus between 1 and 2 is 3 is a true statement. So like we were writing relational symbols in front, we write also a functional symbol in front. So in this case, you can rewrite it closer to logic, that you have x3 and 5. So this is a logic like that you add, this is a function, two-argument function, and this is two-argument relation, and it holds between what is happening, what this function plus does, so you have x plus 3, and this is, and number 5. So if you want to translate that into logic, you have a symbol for relation. So let's say E, I use the symbol E for two-argument relation, equality, and now I use a function f for plus, and I have x 3, 5. So this is almost, we are almost in predicate language, but in our predicate language you don't have numbers, you have constants. So the number 3 in our logic predicate language would be, for example, constant c, and the number 5 would be another constant d, and that would be again a formula which is called atomic formula in predicate language, mathematical statement. That mathematical statement you translate into such a formula. Atomic, why atomic? Because it does not contain any connectives, and it does not contain quantifiers, so it's called atomic. The atomic formulas correspond to propositional variables, like the smallest pieces in propositional logic. So, so there are two things. One is when you have a real statement, you have to identify the relation, and you have to write it, because in logic we write all the symbols in front. So like this is functional notation. That's why you have functional programming. That's straight from this, right? And you write the formulas like that, and the rest is, I'm going to define that. Also, when you have those functions, that piece, you see, this is called a term. So, because you see, what's happening that you know that relation returns true or false. You say that this is true for certain x and not true for the others. But on terms, on function, you can say x plus 3 is just a function. For certain x, when you say 1 plus 2, the function plus would return 3, not a logical value. You need the formula to say that 1 plus 2 equals 3 is a true statement. So we have those terms which represent all these functions in a sense, right? So we say all variables are terms, constants are terms, and if you have already this inductive definition, if you have already terms, you just write the functional symbol in front. See, I have that would be a term, that would be the term, and that would be a term because I wrote the functional symbol in front, and this function is two-argument function. So here you have n terms if f is an argument function, functional symbols, and you have some examples. And formulas, we have, as I already said, we need to have atomic formulas, and then we use, as we did before, all propositional connectives and quantifiers to form the set of all formulas. So an atomic formulas is first, I said, what is atomic formula? This is an example of atomic formula, relational symbol, and here's a term, and this is another term because constants are terms. So in general, atomic formula is R, where that is a relational symbol, and these are terms. And here are some and you see here f, g, c, z, this is the composition of functions. So this is a function, this is a composition of function, this is term, this is formula, and here are two terms, and you have and now the set of formulas is as before. All atomic formulas are formulas, and then you form formulas with propositional connectives, and with quantifiers, look, you can put the quantifier in front. Now, the other things to remember is that quantifier, it's like connective, right? You have a quantifier, and it is a symbol for expression for all. Like this is a symbol of if-then. Now, to say for all natural numbers, all natural numbers are greater than 0, so you have to say for all n. So quantifier comes with the variable. That's the same. And here you have A implies B is a formula. So just this is a sign of implication. Alone is a sign of quantifier. You need to put, to form the formulas, you need to put, and the same for existential, whatever you want, x, y are any variables. So that's why you can put a quantifier which says for all x and for all or exist x. And here you have some examples of formulas. You see, this is a nice formula. You have atomic formula. You put existential quantifier, and then you can put again So that is a formula. You can put negation, and again you can put another quantifier in front. So you have this is a well-formed formula. And the other important notion, if you have a formula like that, see, if you have a formula, for example, there is x, r, x, y, z. R is 3-argument relation. And I can put for all t, r, x, y, z. I can put there is y, r, x, z. I can put for all z. That would be formulas. Now, when you see this variable is connected with this variable. Here, there is no variable. So here you say that this quantifier binds a variable which is inside. Here, there is no variable to bind. And here, I had here x, y, z. I put this quantifier, it bounded this variable, and then I put this quantifier, and I bounded that, and x is 3 variables. And here, if you have a formula with quantifier, but here you have x, y, z are 3. Because there is no quantifier which would bind it. So now we have a notion of free and bounded variables and the quantifiers which bind variables in the formula. Very important notion. So, for example, this does not contain any free. Both variables are bounded. That is a formula without variables, so it's called closed formula or a sentence. And here, okay, I give you an example. Okay, all right. I just want. Okay, so that's the notion of bind and free variables. Sometimes you will see we put those variables in bold. So if you put in bold here, and so that would put the bold in here, so you know what which variables are bounded by what. So now is my joke. I want to tell you this joke because I'm a mathematician, so I can joke. So, for example, mathematician would say all natural numbers are greater than 0 and some integers are equal 1, right? That's a nice statement. That's an even true statement, right? On both, all natural numbers greater than 0 is a true statement. But we like to use symbols instead of writing all these long sentences. So we will say, okay, all. So I can say greater than 0, x greater than 0. So that is a symbol for x greater than 0. All natural numbers is for all x in n. So this is all natural numbers. Sometimes, often, people like to write x greater than 0 for all x natural numbers, to say. So that would write like that with putting symbols. Symbols for greater, symbols for quantifier, and is and. And now some integers are equal 1 would be there is integer, which is 1, and just some integers great equal 1. So that is like throwing symbols, logical symbols and mathematical symbols all together to represent, which is okay. It's like loose writing. You can write even putting the symbols in natural language in more coherent way. So, for example, that could be for all x natural number, x greater than 0, and there is integer. It means y in z is the set of integers, y equal 1. So that is more structured way of representing just that statement, not in logic, but using logical symbols, which we do it is very often. This is a more precise way of representing it. So now there is one thing that in natural mathematics we use quantifiers. We say for all natural numbers is for all x in natural numbers. So the quantifiers like that do not exist in logic. In logic, you can only write x, and you don't know what the x is. Then we will get that the x in a certain universe can be natural numbers, but that is not accepted in logic. So we have, but they are very useful to use. So we introduce in logic quantifiers like that are called quantifiers with restricted domain. So we can use them, but we have to be very careful. What do they mean? So restricted domain, you can write bx is now ax bx, we are in logic, are our formula. So for example, I can write for all x greater than 0 and x natural numbers, and I can write x plus 1 equal 5 implies x squared equal 3. See, I can say that I want this only for that condition. So this is our AX. So it's useful to have such quantifiers, but in logic you cannot write like that. So we say that this represents for all x, AX implies BX. You see, and this is a real good logic formula. Good logic formula. So such formula I can write in this way. And for existential quantifier, there is complex statement bx that becomes, there is x, ax, and bx, and that is a proper logic. So we can replace this if we want to write in our logic, but you have to remember that that is the replacement for such logic formula, and then we will have. Why we have to do it like this? Because when we define the laws of quantifiers, it means when we define the predicate logic tautology, those quantifiers behave differently than our real quantifiers. So all tautologies, you will use our proper quantifiers. The laws for the logic formulas of predicate logic are different than the laws for restricted domain quantifiers. Restricted domain quantifiers. They are very important, they're useful, but we have to remember that you have to, when you reason with them, you have to be more careful. You cannot reason. And these are called transformation rules. So now, if you have a statement, for example, and I want to translate it in the logic formulas, that's I already did examples like that, right? If you have statement like that, you write them close to logic, and then you translate to logic. And now, for example, when you have a mathematical statement, that is nicely written, the statement that all natural numbers are greater than 0, and there is integer which is equal 1, right? So that is still, this is purely mathematical statement written with logical symbols in nice coherent way. And now you can translate it to a pure logic formulas, and you can see to translate that into the predicate logic language, you need to use quantifiers with restricted domain. So now you have at restricted domain quantifiers. Short solution is what? What are the basic statements? The basic statement would be x in n. So x in n corresponds to this, but x in n, this is a real statement. What does it mean? X in n, you have one argument relation. Because one argument relation, it means that x is in n, is true or false. So that corresponds to one argument relation. That corresponds to, this is two argument relation, and I write g for greater, and which is between a variable, and 0 is a constant. So that corresponds to that. Y in z is z, y. I use z to remember that I started with z, it means integer. And equality is equality between y and another constant. And now our statement with restricted domain. That here is, see, with restricted domain, that is too high, right? Is for all nx, gx, c1, and the restriction on the second quantifier was zx. And now this is restricted domain quantifiers formula. And now you use here the restricted domain rules to write a real logic formula. Nx, that would be for all x. N for all nx becomes implication, and there implies connection. And that is a proper formula of our predicate language. Of course, we can ask why the restricted domain quantifiers are defined like that, the transformation rules. All humans are mortal. If I am human, I am mortal. Socrates said that. So all humans mortal. For all x, if x is a human, then x is mortal. So that's why we translate restriction on universal to implication. And and now you have a method of translating mathematical statements into logical formula. Why this is important? When you want to do automatic theorem proving, when you are in AI, you have complex statements, mathematical natural language statements, and you want to do proving of those statements in logic, it means automatically prove, so you need to go to automatic theorem proving systems and so on. You have to translate everything into logic formulas. So you have a nice translation, this translating that, so you have a lot of examples. Now, this is typical translation from natural language, and this is typical in artificial intelligence. For example, any friend of Mary is a friend of John, and Peter is not John's friend, hence Piotr is not Mary's friend. Is it true statement or not? Can you prove this statement true or not? So you have to translate it in a proper way. So when you do now, because before the examples were just mathematical examples. I will give you a simpler example before. Like, for example, and we go to Peter and Mary, which is, I like to start with difficult example. Okay, so let's say, this is similar. Any white bird can fly. And then I want to have, for any bird, one can find some birds that are white and so on, this type of, and you want to write a program which would tell you if it's, what's happening with those flying birds. So when you look at this, you have to look in terms of our predicate language. Any, of course, is for all. Now, what is white is one argument predicate. X is white. To decide that something is white, you have to, it belongs to a set of white things. So it's one argument predicate. Bird is, X is a bird. So it's one argument relation. Can fly is, let's put it F, is can fly is again one argument relation. So you can say, oh, can is relation. What does it mean? Can fly is a relation. So to translate that, you need 3 one-argument relations. And now you can write any. What does it mean, white bread? Any is for all. White bread, bird is white, and bird. So it's white and bird. Can fly is flies. So you translate, this is restricted domain of things which fly to white birds, and that is for all X, white and bird, then flies by restricted domain, and this natural language is translated into such formula. So when you look at this, for any bird, one can find some birds that are white. You have to, these are called, remember, these are called atomic formulas, right? So what would be, here you have bird, you have white, and then you have any bird would be any bird. Now, for any bird, one can find some birds. What it means, for any bird, there is a bird, one can find. Some is there is. Some birds would be that bird which can, what was white, right, which is white. And again, so this for any bird, there is a bird which is white. And then you have the formula, and you have this is a little bit more complicated. Like, for example, translate some patients like all doctors. So here, which are atomic formulas, relations, atomic formulas, is patient is atomic formula, X is a patient. You have doctors, D, X is a doctor, and like is a relation. So you have a relation which goes between two arguments, X likes Y. This is the meaning, natural meaning, and these are the formulas. And there's no propositional connectives. So now you have restricted quantifiers that some patients, what does it mean? There is a patient. Now, all doctors would be for all the X. Now, you can't write X likes a doctor, because doctor is a relation, so you don't have logical value here. So dy is a predicate, not a term, so you cannot write like this. So likes all doctors, you express that for all doctors, X likes all doctors. So X likes Y, but Y is all doctors. So our statement would become, there is a patient that for all doctors, this X, a patient, likes all doctors, Y, but Y is a doctor, and here is a typo. You see? That is okay. I found a little typo in my slide. This is Y. And of course here it's already, well, so I have to correct this typo. I always find some typos. So that is how you translate. And also you have in the next step you do predicate tautologies, but what I want to remark that when you deal with this kind of problems, we use what is called intended interpretation or meaning in an I, or in computer science, that instead of using D X for doctor, you can write doctor X, because D is a symbol, but intended interpretation of that symbol would be a doctor. So you can use, when you live in special universes, you can use the full names and so on, and you can see it. We'll discuss it later. So now we have predicate tautologies. So that all was syntax. Now we have predicate tautologies. Of course, intuition what it is, but formally it's chapter 8. So what are predicate tautologies are called also valid formulas or laws of quantifiers. And we want to be, you can see that here when you have the predicates, you have functions, you need sets, you need a more complex structure than just a truth tables for connective. So the predicate tautologies or semantics are defined in terms of structure, universe, and interpretation. You need universe and you need interpretation, and this is called structure. Because if I write P, X, C, this is just letters. But I can say what it represents, for example, in natural numbers, when P is greater and C is 5. So it means now I want to look at the structure, natural numbers, and this is the universe, and I represent PE. It means interpretation of this. I say that this is greater, and I say that I interpret this constant as 5. So if in this structure, if I interpret P as greater, so I have greater, X is X are natural numbers, and C is 5, so I 5, so that is a statement X greater than 5. So I can represent M in structure. I can have a real statement in a real universe under the interpretation. And for example, if I say here that I have the same C1 and C2, and I have the same interpretation, but C1 is 5 and C2 is 3, I would get a statement here. My C1 was 5, so I would get, and C2 was 3, I would get 5 greater than 3, and I would get a true statement in the structure under that interpretation in that universe. So that's how, and then it gets more complicated. So we define the model structure. It's called the model structure, universe and interpretation. And for a given formula, which can be complex, I can have P Cx implies, and then I have all x and so on. So formula, and I denote AI a statement which is defined when you interpret everything interpret in the given universe. So for example, and that is a very complex definition. You do it by many inductions and so on. But what does it mean? For example, let's have a simple formula, that complex definition, but the intuition is the following, that let's say there is XP, XC. And the model structure, I have M1 and E interpretation. And the universe is here. You have natural numbers. And I interpret P, P E1, I interpret as equality. And C E1, I interpret 5. So in that statement, this is a formula, AI would become in this N would be that there is n in n, because I am in n, and you interpret p as equal, so as n equal 5, right? That formula would become, because that would be equal, and C would be equal and psi, right? So, and that is a true statement. So that formula, corresponding formula in this universe, under this interpretation, is a true statement. You can write just n, but remember that we have that n is a natural number, because our universe was natural numbers. So that formula is a true in the set of natural numbers, but you can also write n in n, because we are now in natural numbers. So that's why you can write. And then you can have another interpretation for the same. Like if you interpret less and 0, you would get under that another interpretation. You have a statement, a formula is there is natural number less than 0. And that we say that in this first case, we say in this case, which we did here, we say that the structure satisfies that formula. So our first structure, M1, this is our M1, you write that this M1 satisfies our formula A, because after this whole interpretation, we got a true statement in that universe. So you say that structure satisfies the formula. If you have another interpretation, that we got a statement which was a false statement, because there is natural number less than 0 is a false statement. So we say that that does not satisfy that structure. M2 does not satisfy that formula, and it's called a contramodel. So, for example, there's another, you have yet another structure. So now you have integers in the set of integers. So when you look at this, now you can do it fast, right? Because if you have the model structure, which is the same, M3 is ZE3, that PE3 I take less, and CE3 is 0, and I have a statement, there is X, P, X, C. So when you look at this, you can write immediately, you have Z, so there is X in Z, P was less, 0, X less than 0. That is a true statement. So M3 is a model of our formula A. So you can see the same formula, depending on the structure, can be true or not true. Some structures are models, some structures are not models. So because at the end you have a true mathematical statement, or not only mathematical. There is a question, what happened, when you have here, you have, for example, y, so you have to sort of handle that, and we do handle that. And I gave you an example, more or less, how. Now you can have a more complex formula for all there exist. So, and now when you look that my structure natural numbers and relation R is less equal, and so you will get what a formula corresponding to that formula would be. There is a natural number, because we are in natural numbers, such that for all y would be all natural numbers, x less equal 1. Again, that is a true statement, and it also says that there is a smallest element. There is a smallest element in the set of natural numbers, which is true. It is 0, so it's true in that structure is a model for that formula, so it gets more complicated. And rigorous definition is in chapter 8, and it's really a little bit. It's a little bit. You have to do a lot of details, but also now we can define a tautology. We say that any formula of predicate language is predicate tautology if all structures satisfy A. So it means what? It is for under any interpretation in any universe, it's always true. So it means wherever you are, in mathematics, in physics, in life, you can always use those formulas as the way of reasoning, because you know that whatever happens, whatever you interpret, is always true. So, and it's not predicate tautology if there is a model structure which does not satisfy, that is called a contramodel. And and to show that something is not predicate tautology, you have to show a contramodel. And you have a basic tautology. Notation. Often in the books for predicate tautologies, formula is predicate tautology. We say that formula is valid. So you replace the name tautology by valid in order to use the name tautology only for propositional tautology. We use the word tautology for both predicate and propositional, but we say it is a predicate tautology. And if you want to distinguish when there is a confusion, you write out predicate tautology. And for example, this is a predicate tautology. And then this is not predicate tautology because we can find a contramodel, and the contramodel would be, for example, a concrete formula. Let's say that the formula is Pxc, and we define a structure, natural numbers, when P is less and C is 3, and it would be that there is natural number less than 3, then all natural numbers would be less than 3, which is a false mathematical statement in natural numbers, so that is a contramodel for that. This is not a predicate tautology. And then you have a basic laws of quantifiers, and of course you also have I discuss a little bit the laws. Oh, okay, no, I'm going back. I'm going to discuss that. You know, going back to restricted domain quantifiers, because this is a good moment, that you know, this is the most basic predicate tautology. Now, when you replace that by restricted domain, so it's like, oh, this is always. Yes, this is always for normal quantifier. If you replace x by restricted domain quantifier, this is not a predicate tautology. So that it's important that you have to be careful where you use restricted domain. And why? Because that formula translates into this formula in logic, and this is not a predicate tautology. And I give you a counterexample here. So it's the same, and that is a nicer counterexample. So again, but you can say that if you have, this is a basic predicate tautology, if you have restricted domain, that you have, this is a restricted domain quantifier, you see, restricted domain quantifier tautology corresponding to that. So if you want to have restricted, if you want to write there is bxax, you have to say there is an x, then there is bx, and that you prove that that is a tautology. So just that from the beginning to make you aware that when you reason with restricted domain, you have to be more careful, and you cannot assume, oh, I know that, it would be the same. It isn't. And now we have a special quantifiers laws. So, for example, you have, I want to give you a list. Oh, let's do important laws of quantifiers involve equivalence. So we say that two formulas are logically equivalent if and only if is a predicate tautology or predicate tautology. So you can write the Morgan laws is that instead of writing if and only if, you use the logical equivalence. So the negation of universal is existential negation, and so on. And also you have definability of quantifiers through the Morgan law. You can prove that for all ax is logically equivalent to dot dot. The same, there is x is not for all dot x. So it means that really in predicate logic you can have only one quantifier and define the other quantifier in the terms of the one you assume. But we assume that we wanted to have two. And then there is renaming the variables. Like, for example, for all xax, you can replace x by any y, and the same for universal. You have the alternation of quantifiers. X, y is the same as yx, logically equivalent. And then you have introduction and elimination laws that you can have for all x, where b here is a formula which does not contain a free variable x. You see, this x binds that, but x is non-existent, so you can distribute this over that and keep b, and the same for universal, and the same for conjunction, and the same for existential. Introduction and elimination laws. This is b. B is again no variable x. If you want to introduce or eliminate x, for all x changes into there exists changes into. So you have a basic laws which you use and you have to know. Also, you have distributivity laws, which are very important, that when b, both formulas have a variable, so this quantifier binds x in both, you can distribute universal quantifier over conjunction, and you have distribute existential over disjunction. Very nice. But you don't have it, the full distributivity does not hold for disjunction, and here the full distributivity does not hold here for conjunction, and I give you examples. And also I here restricted domain quantifiers holds. That's fortunately. You can negate restricted domain exactly the same as you did the normal, and here's the proof. How you prove? You want to see what's happening here. You rewrite this by normal formulas, so that would be bx implies ax. Now you are in normal formula of predicate logic, so you can use the Morgan law. So, oh no, what I do, I change the implication. B implies implication is not B or A, so I change the implication into not B or A. And now I do the Morgan law. So that would be for all x negation of that whole formula. And now here I have negation of this junction. The Morgan law would be this negation becomes double negation, that becomes conjunction, and you have this. And now double negation by laws of propositional law, double negation is also B. And now, and that I will get Bx and not Ax. And that, by definition of our restrictive, is this. So I prove that law. You can prove the other law by yourself. And that's it. We will have all those proofs of everything I told you later. But now you can use those laws and remember them, and we will be careful with restricted domain quantifiers. Thank you very much.